Welcome to This Explainer. Today we're going on a seriously fascinating journey into how science actually makes sense of our vast, complex world. We're going to break down the massive, the microscopic, and the incredibly dangerous, all by decoding how we make the invisible visible.
It really brings up a fundamental question, right? How do we study things we can't even see? Human perception is amazing, for sure, but it is limited. We can't see the tiny atoms that make up our bodies, nor can we just zoom out to view the entirety of the Milky Way galaxy in a single glance. We can't easily peer inside a raging volcano or safely stand inside a building during a major earthquake just to see what happens. So, how do scientists understand these extreme scales and perilous events?
Well, here's our roadmap for today. We'll start with unlocking the unseen, move on to tackling extremes in scale, look at predicting the perilous, break down the 4 types of models, and finally, look at the limits of models.
All right, part 1, unlocking the unseen, and defining what I like to call the ultimate scientific tool.
So what exactly is a scientific model? Well, it's a representation of an object, a process, a system, or even an idea that helps us explain or understand a scientific concept. The absolutely crucial word there is representation. It is not the real object itself. It's a simplified version. It might be scaled way down, scaled way up, drawn out, calculated, or simulated on a computer. But its entire purpose is to help us study and explain the real thing without needing the real thing sitting right in front of us.
Let's ground this in a real everyday experience. Picture this. Someone sprays a bottle of perfume in one corner of a room. You wait a few minutes, and suddenly, people all the way at the back of the room start to smell it. Now, obviously, you didn't see anything physically travel across the room. Those particles are totally invisible to the naked eye, but you absolutely experience the result.
So, what invisible phenomenon is actually going on here? Well, it's the movement, the spreading of those tiny perfume particles through the air. We can't see the literal journey those particles took, but by using what's called a particle model, scientists can map out and explain exactly how those invisible pieces move, how they bump into each other, and how they spread out in different directions.
And this brilliantly illustrates how models help us explain the microscopic world. Things like atoms, molecules, and bacteria, they're just way too small for our naked eyes to catch. But particle models give us a way to visualize their behavior. Take a basic atom model, for example. You literally can't see an atom, but an atom model cleanly maps out the parts we can't see: the nucleus, the protons, the neutrons, the electrons. It gives us a visual building block for all of matter.
Moving on to part 2, tackling extremes in scale. Going from the micro to the macro. Okay, so on one hand, you have the actual real Earth. It is incomprehensibly massive, wildly complex, and far too huge to observe as a whole, well, unless you're an astronaut floating out in deep space. But on the other hand, you have a physical globe. The globe is a simplified model. Sure, it doesn't show you the real size of mountains or every single building, but it perfectly allows us to grasp the Earth's overall shape, the layout of the continents and oceans, and basic geographical directions.
It's actually pretty amazing when you really stop to think about it. Models literally allow us to hold the entire solar system right in the palm of our hand. By scaling down the mind-boggling distances between planets, a simple classroom solar system model gives us an immediate visual understanding of planetary order and orbits that would otherwise be completely impossible to perceive.
Which brings us to part 3, predicting the perilous and staying safe from the extreme.
Because models aren't just about understanding scale. A lot of the time, they are literally about survival. Some phenomena are simply way too dangerous to study up close. You wouldn't want to go stand in the middle of a typhoon just to see how fast the wind is blowing, right? For earthquakes, scientists use simulations to understand how the ground is going to shake and how buildings might react, all without putting a single person at actual real-world risk. For typhoons, computer simulations crunch weather data to predict possible storm paths, which helps local officials decide exactly when to order evacuations. And for floods, communities use hazard maps to identify at-risk areas so they can plan safe evacuation routes long before the heavy rains even start.
Think about this real-world application for a second. Would you ever test a newly built bridge's strength by just getting in your car and driving over it? I really hope not. That would be incredibly dangerous. We simply don't rely on trial and error when lives are on the line.
Instead, engineers use mathematical models. These super complex calculations to test bridge loads and predict possible structural failures. By plugging different variables into these models, they find problems early, design safer structures, and protect lives before a single physical brick is even laid down.
All right, part 4, 4 types of models. Let's categorize this scientific toolkit.
We can actually organize all these incredible tools into a pretty clear framework. First up, we have physical models. These are the 3D objects you can physically touch or look at, like a globe or a plastic model of a human heart. Second, we have conceptual models. These use drawings, words, or ideas to explain how things work. Think of a diagram of a food chain or the water cycle. Third, mathematical models. These use numbers and formulas to predict outcomes, like those bridge load calculations we just talked about, or a graph showing weather patterns. And finally, simulations. These are mostly computer-based models that show change over time, like an animation tracking a typhoon's path.
Now, what's really fascinating here is the difference between a drawing and a simulation. A conceptual model, like a drawing of an atom on a chalkboard, is a static, still representation. It's great for showing the parts. But a simulation, like a computer app mapping the solar system, shows dynamic movement and change over time. They're both models, but they serve entirely different analytical purposes, depending on whether we need to understand a static structure or an active, moving behavior.
And that brings us to part 5, the limits of models and why models aren't perfect truths.
Because as brilliant as all these tools are, we need a quick reality check here. Models are never perfect. They are incredible tools, sure, but simplification always comes with a trade-off. By focusing on the specific parts we want to study, we inherently have to leave out some of the other messy complexities of the real world.
Let's look at those high-stakes examples again, side by side. A typhoon simulation is invaluable for preparation. It gives us a really solid, data-driven prediction. But the actual storm might still change course unexpectedly. The model is a forecast, it's not a crystal ball. Similarly, a mathematical model of a bridge helps predict safety and structural integrity with really high accuracy. But that model doesn't replace reality. Engineers still absolutely require real-world, physical safety checks and inspections once the bridge is built to account for actual wear and tear.
The fundamental reality of these scientific tools is that they're always evolving. A model does not, and honestly cannot, show every single thing about the real object. It is only a simplified representation based on the data we currently have. And because science is an active, ongoing process, whenever scientists collect new evidence or get better data, they go right back in and improve their models. The models grow and adapt right alongside our understanding.
Wow, we've covered a lot of ground today. From the invisible perfume particles floating through a room to the massive, complex calculations that keep our bridges standing. Models are the crucial bridge between human limitation and universal understanding. So, I'll leave you with this to ponder. Looking at the world around you today, what unseen phenomenon will you try to model next? Thanks so much for joining me on this explainer, and keep learning.